Hi, I hope this video finds you well. Today we will be covering the subarray sum equals k problem. The problem description is simple. We're given an array of integers called nums, and we're also given an integer called k, and our task is to return the total number of subarrays whose sum is equivalent to the parameter k. And of course, it provides a definition for what a contiguous subarray is, and as we see, it is but a contiguous non-empty sequence of elements. So you look at the problem statement and you almost you notice a couple patterns. And the first pattern is that you're asked for you're asked to find a subarray or subarrays, and you're also given the k here. And this almost matches the tune of many other sliding window problems that ask us to do more or less the same. One question asks to do the minimum size subarray sum. The other is subarray product less than k, or shortest subarray with sum at least k. And so, this matches the tune of the questions that would want us to apply the sliding window technique. And so it's natural to almost jump to the template for what a sliding window technique would look like. But the exception here is that we're provided a constraint, and the constraint is that the numbers within our input array nums can in fact be negative. And so the main takeaway here is that if you have negative numbers within your range, then the sliding window technique quickly becomes redundant. So you can't use the sliding or sometimes also called the stretching window technique when there are negative numbers in the array, because the sum doesn't grow monotonically with the window size. So what does this really mean? What this means is that if we have positive numbers, as we expand our window, as we move the right pointer upwards, the sum would actually increase. And then, of course, if the invariant is not upheld, then we can contract the window from the left. But you would imagine that as we expand the window, the sum would only get bigger because we're adding numbers to a specific number. But with negative numbers, if we're adding positive numbers and suddenly we encounter a negative number, that number will then become very small. So, it sort of distorts the pattern that we have here, and we'll look more into why we can't use the sliding window technique here. Let's consider an array with 3 entries, and of course, with sliding windows, it's very popular or common, or in fact needed, to have 2 pointers, a left and right, both planted at the head first, or really the first entry in the array. And we're given a target of 4, and the sum so far is 0. So what's going to happen as we use the sliding window approach is we're going to register a target, and we're going to register our sum, which is 0 at the moment. And we're going to ask ourselves whether the current sum, which would be 5, whether this is equivalent, whether this meets our target constraint. And we can see that it doesn't. The target is 4, left and right both rest at 5. So naturally, we would move the left pointer up, and in fact, the right pointer would also be moved up. And so this is our way of, sort of reconfiguring what we want to start at. And so this would be common within any sliding window algorithm. We would quickly ignore that redundant element that does not give us the target. But what we've done inadvertently is we've actually ignored a subarray that actually does add up to the target. As you can see, 5 and -1 would give us the target of 4, but the sliding window algorithm, the popular sliding window algorithm, has disregarded that subarray. So we're not going to use the sliding window approach here. Instead, we're going to look at another approach that actually uses some auxiliary space. And this is a very common theme. We will reduce quadratic time to linear time by trading time for space. And so we're going to introduce some data structures here that will help us with this. So first, let's consider a very simple, straightforward array. And we're not going to focus too much on the elements, what the elements are. I'm just going to put an asterisk there. And you can imagine that a certain subarray will add to 8, let's suppose, hypothetically. And then a section of that subarray, we'll say a subarray almost, will add to 5. Then this means that the elements between both of these red subarrays, it would mean that the subarray that rests between them must add to 3. And we're assuming that our target is 3. So 8 is essentially the, we can think of 8 as the running sum. So, we're adding numbers as we move. And at every single element, we ask ourselves, can we subtract off the target, which is k? And does what we subtracted off, does the difference exist? Are there elements within the array that add up to the difference? So in this case, we had 8 as our running sum, and we're just moving along the array, and 8 has stopped and asked itself, can I subtract off k, which is 3? Can I subtract off k? And do I have a subarray somewhere in the past that adds up to this quantity, this difference? And if the answer is yes, then this validates, it verifies that there is a subarray between both of these red subarrays that add up to the target. So really what this is trying to say here is, if we can take the current running sum and subtract the target and verify that there are elements in the array that add up to this difference that we have gathered from subtracting the current sum from the target, then that means that we can verify that a subarray exists that add up to the target. So this is a verification process. If we can take the greater part and subtract the smaller part, and if that smaller part exists, then the intermediary part also exists. Here's another example to sort of hammer in the point. Here we kept a running sum of 6, right? And we've reached sort of the end here at the very tail. And here our running sum is 6, and we ask ourselves, can we subtract off a sum or a target? And is there a subarray in the past somewhere that actually gives us a sum that is equivalent to the difference? And the answer here would be yes. If we take 6 and we subtract off 4, there exists not one but 2 subarrays that add up to that difference. And so if that's the case, that means this verifies that there are subarrays that also add up to the target. And so here there are actually not 1 but 2. So how many subarrays would add up? How many subarrays would there be that would equal the target? Well, there would be 2, right? Because we have 1 subarray that basically this relation that we described before, which is that if we take the greater whole and we subtract a portion of it, does the result of that exist? This relation that we have verified happens 2 times. So there are 2 subarrays, which means there will be 2 corresponding subarrays that will add up to the target. If there were 3, then there would be 3 subarrays that add up to the target. So we have to create some sort of data structure, or we have to introduce a data structure that will store the frequency of the sum of subarrays. And then for the running sum, in this case it was 6, in the previous case it was 8, we ask ourselves, can we subtract off the target, and does a subarray exist somewhere in the past, or do multiple subarrays exist somewhere in the past that add up to the difference of doing the current sum minus the target? If that is the case, then we know that there are X number of subarrays that exist that add up to the target. That will be equivalent to the frequency of how many subarrays appeared as the difference. So let's get into code here. We're going to introduce our solution and of course our method signature. And we're going to have a hash map. And again, this hash map is going to store the sum of each subarray, and the frequency, what will be the value? The value will be the frequency that matches that given sum. We're going to put 0 and 1 as an entry into our hash map to begin with. For 0 subarrays, there's 1 occurrence if we haven't started yet. And we're going to introduce 2 more variables, sum and answer. Sum will store the running sum as we move forward. Answer will actually store how many subarrays matched our condition. We're going to open up a for loop, and this for loop is going to first, it's going to sort of aggregate what the sum is, right? This is what is called the accumulator pattern. It will accumulate the sum as we move forward. And as we said before, our main objective was to store the difference, right? So for each, as we add the running sum, we're gonna store a difference. The difference will be sum minus the target that we want. And if it is the case that this difference has already occurred, that means that there are elements in the past that add up to our difference, right? And that would mean that our target, if that is true, then there are elements that add up to our target that rest between them. And so how many times should how many such arrays are there that add up to the target? Well, that will be equivalent to how many subarrays matched the difference, right? So we're going to go back into the map, and then we're going to get how many times or how many subarrays there were that added up to the difference. And of course, irrespective of whether or not we find find subarrays that add up to that difference, irrespective of whether or not that's true, we still want to store the frequency of our sum. So this is our way of preparing us for for the next iteration, right? So really, I mean, this algorithm can be boiled down to having a running sum, asking ourselves, can we take the running sum minus the difference, and do elements exist in the past that add up to that difference? If it is, then that verifies that our target subarray also exists. How many target subarrays will there be? Well, there will be X target subarrays, where X is the frequency of how many subarrays added to the difference. And then, of course, we return answer.